Hello YouTube. Today I'm going to show you how to do a simulation of the BJT common emitter amplifier in Qucs, which is an open source circuit simulator. So what we're going to be simulating today is the operating point, which is going to be the ICEQ, or ICQ rather, and VCEQ, which is the current going into the collector. So ICEQ, this is collector, base emitter, and we're going to be taking and simulating the VCEQ, which will be fairly easy to do as well. We're going to be using the circuit or the transistor properties of the 2N222, which can be found online. So when you're putting together your circuit, you're going to want to use the components, and you're going to want to go down to non-linear components, and you're going to want to add a transistor, which in this case is the BJT NPN, and you're going to want to double click on that and change all the properties in here to fit what you find if you Google it. So as you can see, I've Googled it already. I've got the 2N222a.lib file for pspice, and these parameters you're going to want to set, so IS, BF, and so on are in here, and you're going to want to set them to whatever it is in here, because that's your best guess of what the actual circuit will behave, how it will behave. So once you've done that, which is a very tedious process, you should probably save that transistor so you can use it again, because most people don't use different circuits, transistors very much. So you're probably going to be using the same BJT several times over. You're going to want to change those parameters. Another thing is when you put in a signal source in QCS, you will probably see that it'll give you a huge frequency. So as you can see, 1 volt, which is huge anyway, but you'll see here frequency is 1 gigahertz. You're going to want to probably do 1 kHz in most cases, at least for this BJT. So that's what I have here. I'm putting in a 15 millivolt peak, and I'm putting in at 1 kilohertz. So anyway, so once you've built your circuit, and as you can see, I can have my voltage source, we're going to start simulating it. So to start simulating it, you're going to want to go to Simulations here in the Components tab on your side. You're going to want to put down here a DC simulation. You don't have to change any of the parameters in the DC simulation, but I'll show them to you anyway. So you shouldn't have to change any of these, but if you need to, or you think you need to, you could. Now you're going to want to you're going to want to go to probes here, and you're going to want a current probe. So we're going to place that current probe, we're going to rotate that current probe, and then we're going to place that current probe in our circuit so that it's measuring the DC current flowing into the collector. And as you see, I didn't put it down here on this branch here. I could have, but it won't matter in this case because there's no DC current flowing through the capacitor. Of course, you should know that. Maybe you should know that. So that is good. So we can actually do, with this, we can do our DC bias. So if we go up to Simulate, Calculate DC bias, we can have our ICQ is about 6 milliamps, and our VCEQ is about 4 volts rather. If I did that calculation correctly, I can always bring it up here. So we have 9.197 or so minus 4.946. So it's about 4.251. Obviously, I don't have the calculations to do the comparison of what it's actually supposed to be, but we should assume that, well, we can't really assume that that is not accurate. You want to check it with the numbers that you calculated originally by hand or with a with a software package, calculation package. Okay, so now that we've determined our operating point, we don't really need this current probe, we'll just leave it anyway. So we're going to want to do our transient response and our frequency response. So we're going to do first our transient response. So to do that, the easiest way I find is that to label these nodes here. So this node we're going to call V in. In this node here, we're going to call V out. So V out. In order to change the name, you can just double click on it. Just double click on the wire and it'll allow you to change the name. Okay, so now that we've done that, we're going to want to go back to simulation and we're going to want to do our transient response. So in our transient response, we're going to want to double click on that. And we're probably going to want to raise this because we have a 1 kilohertz input. So in this case, we want to do probably like 5 milliseconds. Of course, you can easily do the calculation 1 over frequency, right? So whatever that is, however many revolutions you want to do, that'll work fine. The step size you'll probably want to change. This is going to look really, really bad with this step size, 500 micro. It's going to look nothing like a sine wave, even though it is a sine wave input. I will show you what it looks like if you don't have the step size correct. So if I simulate this and I add a graph here, so when we're adding a graph, you're going to want to look here on the, so as you can see, we have the vin.v of t, so that's the voltage with time, and as you can see here, the x-axis is time, which is what you want. We're going to plot V out first. Click apply OK. And as you can see, that looks nothing like a sine wave. So we're going to put our input now on a separate graph. V in, apply, OK. And as you can see, our input also looks nothing like a sine wave. And the reason this is because our transient response here, our step size is way too big. So we're not taking samples quick enough. So if we want to do a good, good thing, we might want to try like 10, so 501 samples from our circuit. There we go. Now you can see we have a good sine wave input here, and we've got a good sine wave output here. So that pretty much gives us the transient response. The reason why I did 2 different ones here is because, as you can see, we have almost 3 volts here. Not quite, but almost 3 volts. And actually, we could do a little marker here. So this is 2.76. And this is a little bit down because there's a little bit of distortion, but this is negative 2.87. So it's not perfect. And this is obviously 15 millivolts because that's what we did. As you can see, there's a little bit of jaggediness. If you want to remove any of that jaggediness, you're going to have to increase the or decrease the step or increase the number. I usually fiddle with the step personally, but you could do either or. So now what you're going to want to do is now that we've done that, we're going to want to do the frequency response. So we're going to go back down to simulation, and we're going to add a AC simulation right here. And as you can see, that's there. So now we're going to have to edit these properties. These are huge here. The start frequency is 1 gigahertz. You're not going to want that. You're going to want like maybe 10 hertz or maybe 1 hertz, which is what we have. So now we're going to want to do maybe a megahertz. We're going to probably want to go to like a megahertz, maybe 1 megahertz. The step size, you're going to want a lot smaller than this. You're going to probably want like maybe 100 of a step size or 1,000 of step size, so 1K. You could maybe do But one, this is the step size of that. What you're also going to want to do is we're going to want to do, because this is frequency, we're going to want to do a logarithmic here, type logarithmic, and this is says changes here, points per decade, so however many points per decade. Roads are going to do 100 points per decade. Maybe we'll do 1,000. No, we'll do 100. 100 points per decade is probably okay. So now that that's done, we're going to want to add because we're doing the simulation already. It's doing the simulation, it's gathering the data. The problem is that we don't have any way of getting the gain, and the gain is obviously an equation. So you're going to want to go up here to insert equation, and then we're going to want to double click on the equation, and we're going to want to call this something. I'm going to call it gain because we only have one gain, but if you had more than one gain, obviously that's going to be a problem. So to do the AC simulation, we're going to want to do dB, so this is the gain, and it's obviously V out over V in, so V out dot V divided by V in dot V. Click apply, click OK, and now that there's our thing of gain, so we're going to click simulate. Now we're going to want to add another one of these. Okay. Now this is where these labels come very, very in handy. As you can see, this is AC frequency over here. So this is the frequency response of the circuit. And as you can see, we have this gain here, and that's correlating with our circuit, with our equation that we defined. So you're going to want to double click on the gain here and add that to there, so that it's in our graph like we did before. And click apply, and click OK. As you can see, it's very, very, that, which you can't really read. You can't, and the reason that is because this is a linear axis. So we're going to want to double click on this again, and we're going to go under properties and logarithmic x-axis grid. Click apply, click OK. There we go. There is our frequency response of our circuit. So if we want to know like our 3 dB point, there's no easy way of doing this. Of course, you can look at the graph, and that's what I usually do. But the first thing you want to do if you're wanting to demonstrate, I suppose, your frequency response, is you're going to want to find out what your top is. So the gain of 45.6, as you can see here. And then we're going to want to do a simple calculation. So we're going to look for around 42. 42 is not in our list. You can actually extend this. If you extend this enough, it'll start adding points. So as you can see, this is 45. We want around 42.6. So maybe here or so. Click on that. So that's 42.6. And AC frequency of 20.9. Now, that may or may not be good, depending upon what your application is. So you're going to have to determine if that matters. But that's how you basically ballpark it here. Of course, it's easy to determine what the frequency response is just based off this graph. So it's really not an issue, but if you wanted like extreme precision, it may be a little bit difficult in this situation, or at least the way I do it. So I guess keep that in mind. So it looks like that is about it. So you can see that our frequency response is very good. Obviously we start tapering off at a gigahertz, a little bit before gigahertz, or not a gigahertz, but a megahertz frequency. And our dB point, 3 dB point, is around 20 hertz, 21 hertz, which isn't bad, isn't great, but isn't bad for a BJT simulation or BJT thing. So I think that's about it. So yeah, if you have any questions, leave it in the comments. The only reason why I'm doing this is because I hate PSpice and I want to stay away from, I prefer open source solutions. So if you have any circuit or fun open source applications that you would like me to help you with, maybe, or me to do a tutorial, I can do that, perhaps. And if you've got any questions about Qucs, leave them in the comments, and I might make a video. If you've got a circuit that you want me to describe how to simulate or whatever, I can do that as well. I'll leave this in the description, so this simulated version, so you can look at it and take pieces from it. And that's it. Thank you for watching.